To provide Navy harbors with the best possible oil spill removal systems, including operational procedures and techniques, the Civil Engineering Laboratory is developing, testing, and evaluating oil spill removal recovery equipment and procedures. This three-phase program is sponsored by the Naval Facilities Engineering Command. Phase 1 of the program, completed during fiscal year 1973 and documented in a previous film report, identified the best commercially available off-the-shelf equipment. This equipment was then assembled into two different removal recovery systems, one for confined harbor areas and one for open harbor areas. Both systems were successfully tested in Long Beach Harbor. Phase 2 was completed in fiscal year 1976 and is documented in this report. Its objectives were to develop standard performance testing procedures and techniques for booms and skimmers, improve the performance of booms and skimmers, and develop support equipment for deploying and retrieving booms. Tests were conducted on containment boom support equipment at Murphy Pacific Marine Salvage Company, Emeryville, California. The booms used in these tests were the Class 3 Bennett boom and Kepner sea curtain. The major item of support equipment evaluated was the power assistance unit. A gasoline-powered device, it employs 4 low-pressure tires. For boom deployment, the power assistance unit operates in a freewheeling mode. For boom retrieval, the weight of the boom provides sufficient traction for easy operation. For an effective oil spill removal recovery system, the containment boom must have the capability of rapid deployment. It was found that these booms could be handled easily and rapidly by 5 men, 4 on the pier and 1 in a utility boat. Murphy Pacific Marine Salvage Company also evaluated the LD-9 fiberglass aircraft container for use in stowing the containment boom. The purpose of the test was to determine the capacity of the container and the best stowing method. It was found that 450 feet of Bennett or 250 feet of Kepner sea curtain Class 3 booms could be stored in the LD-9 container. Tests were also conducted on a hinged plywood container. On the basis of durability, the LD-9 aircraft cargo container was considered superior. Tests at the Shell Development Company's wave tank, Houston, Texas, were conducted to develop and validate standard test procedures for later use at the Environmental Protection Agency's Onset facility, the Oil and Hazardous Materials Simulated Environmental Test Tank in Leonardo, New Jersey. Standard test procedures to determine the oil containment capability of booms in a catenary configuration were developed and validated using the newly designed Aqua Fence boom. 25 gallons of oil were poured on the water downstream of the boom. Then the boom was towed down the tank. Tow speeds varied from 0.8 of a knot to 1 7/10 of a knot. Wave heights varied from 0 to 1 2/10 of a foot. The quantity of oil remaining within the boom at the end of each run was measured to determine the oil loss rate. Oil escaped from the boom by both flowing under it and by being splashed over it. At the Southwest Research Institute, San Antonio, Texas, a model of an improved boom with a frontal screen was tested. The purpose of the screen is to dissipate the kinetic energy of the oncoming stream, thereby reducing the quantity of oil lost under the boom by entrainment of oil droplets into the water. The model boom was free to react with the waves. It was found that the screen did improve the capability of the boom to contain oil. After completing the laboratory tests on the model boom with the energy-dissipating frontal screen, the Southwest Research Institute fabricated a full-size prototype model 3 feet high and 85 feet long for testing in the Southwest Wave Tank, Corpus Christi, Texas. 2 screens, one with approximately 8 openings per inch, and one with approximately 20 openings per inch were tested. Each screen was held in place by securing it to the bottom of the boom and to the far side of the outrigger floats. 17.5 gallons of oil were applied to the water surface downstream of the boom. For testing, the boom was towed in a catenary configuration with a 25-foot opening at speeds up to 2 knots and with wave heights up to 2 feet. The test showed the screen having 8 openings per inch enabled the boom to contain more oil than the finer screen and the boom without a screen. The final series of tests on booms was conducted at the Environmental Protection Agency's Omset facility. The test tank is 670 feet long, 65 feet wide, and has a nominal water depth of 8 feet. The wave generator consists of 2 flaps which move forward and back in phase to generate regular waves or 180 degrees out of phase to generate random waves. Both the prototype Southwest Research Institute boom and the Bennett boom were tested at Omset without waves and in random waves. 150 gallons of number 2 oil were applied to the water surface downstream of the boom being tested. The booms were then towed in both the head seas and following seas conditions at tow speeds up to 1 7/10 knots and with random waves up to 1.5 feet high. The boom tests were conducted with the standard towing attachment designed by the Civil Engineering Laboratory. At the end of each run, the oil remaining within the boom was hosed into a floating weir skimmer, from which it was pumped into measuring containers. The Bennett boom underwent a similar series of tests. Flotation on the Bennett boom is provided by semi-cylindrical flotation logs placed on both sides of the boom. Tests showed that the Southwest Research Institute boom had better oil containment capability than the Bennett boom. In 0 waves, the Bennett boom started to lose oil at 3/4 of a knot, whereas the Southwest Research Institute boom did not start to lose oil until 1 knot was reached. When the booms started to lose oil, the Southwest Research Institute boom lost oil at a slower rate than the Bennett boom. In 1-foot waves, in the following seas condition, the Bennett boom started to lose oil at 4/10 of a knot. However, the Southwest boom started to lose oil at about 3/4 of a knot. In the head seas condition, both booms exhibited comparable performance, starting to lose oil at less than 4/10 of a knot. Standard test procedures for skimmers were also developed and validated at the Shell Development Company's wave tank. The Marco 1 skimmer, which employs an oleophilic belt, was used to develop and validate test procedures for large skimmers. As the skimmer advances, the rotating oleophilic belt picks up oil, which flows into the entrance of the skimmer. The belt carries the oil to a wringer, where it is squeezed out, with the oil falling into a collection tank. Water passes through the belt. A blend of Navy distillate and Navy special fuel oil was used in all the tests. A plastic sheet guided the oil from a set of nozzles gently onto the water surface. This method minimized the quantity of oil entering the water column. Standard test procedures for medium skimmers were developed using the dynamic inclined plane type JBF DIP 1001 skimmer. Here, an inverted belt guides the oil beneath the water surface. Upon leaving the end of the belt, the oil rises into a collection well from which it is later pumped. In this test, the DIP 1001 was towed at 1/2 knot with 1/2 foot waves. At the end of each run, the oil was transferred into measuring containers to determine the oil collection rate and the throughput efficiency, or the percentage of oil encountered which is collected. The DIP 1001 was operated in both an advancing and stationary mode. In the latter, the oil was placed within a boomed enclosure, and the oil collection rate and the collection efficiency, the percentage of oil contained in the collected oil-water mixture, were measured. The DIP 1001 was also operated in the presence of waves. Standard test procedures for stationary small skimmers were developed using the self-adjusting Weir-type slurp skimmer. The tests were performed at pumping rates up to 62 gallons per minute and oil slick thicknesses up to 1 inch. It was found that at constant oil slick thickness, oil collection rate increases, but collection efficiency decreases as pumping rate increases. At constant pumping rates, both oil collection rate and collection efficiency increase as oil slick thickness increases. At a pumping rate of 62 gallons per minute and with a 1-inch thick slick, the collection rate was 26 gallons per minute and the collection efficiency was 43%. With a 1/3 of an inch slick, the collection rate fell to 7 gallons per minute and the collection efficiency fell to 11%. At the Southwest Research Institute, tests were conducted on a laboratory scale model of the dynamic inclined plane type skimmer. The objective was to improve the performance of equipment of this type. The following operating parameters were varied: belt speed, belt angle, backplate opening, use of cleats on the belt, and use of a stern propeller to induce flow through the skimmer. It was found that cleats on the belt and the stern propeller did not improve performance significantly. The optimum belt angle was found to be 23 degrees, the angle presently used on the JBF dip skimmers. Both belt speed and backplate opening had significant effects on performance. At onset, the major objective of the tests on the JBF DIP 1001 was to determine the optimum values of belt speed and backplate opening. For the test in the advancing mode, booms were placed on each side of the skimmer to contain the oil and produce a uniform slick. With the DIP 1001 being towed at 1/2 knot, the average thickness of the oil was approximately 2 4/10 millimeters. During each run, the oil collected by the skimmer was pumped into measuring containers. The best performance, obtained with a belt speed of 24 RPM and a backplate opening of either 2 or 6 inches, was a 2 7/10 gallons per minute oil recovery rate and 42% throughput efficiency. That is, the percentage of oil encountered which was collected. Underwater photography and video were used to determine where the oil which did not enter the collection well was going. A mist was seen escaping from the bottom plate area, and bubbles were exiting through the back plate opening. It is thought that the mist and bubbles contain a significant quantity of oil. The DIP 1001 was also tested in a stationary mode, with the Bennett boom attached to it in an open trapezoidal configuration. 1.5 gallons of number 2 oil were applied to the surface. Had this quantity spread over the containment area, it would have been about 1 millimeter thick. In this mode, the oil was hosed into the skimmer with care being taken to prevent the water from impinging on the oil to form an emulsion. At the entrance of the skimmer, the oil thickness was about 16.5 millimeters. The test showed that the slowest belt rotation speed, 17 6/10 RPM, resulted in a minimal oil collection rate, 3 4/10 gallons per minute. But a maximum recovery efficiency, that is, the percentage of oil hosed into the skimmer which was recovered, was in this case 84%. Conversely, when the belt was run at maximum speed, 55 RPM, the oil collection rate was maximum, 10 1/10 gallons per minute, but the recovery efficiency dropped to 59%. It was noted during the tests that bubbles and an oil slick appeared behind the skimmer. All tests of the larger BIP 3001 were conducted at a towing speed of 1 knot and with a slick thickness of 1 millimeter. The collected oil was pumped into calibrated containers, which were later drained from the bottom to remove as much water as practical. The remaining oil and water was mixed with an electrically powered mixer. The oil-water samples were taken to be centrifuged at the OMSET Chemical Laboratory for oil containment determination. This procedure was used in all the boom and skimmer tests at OMSET. The best performance in no waves was an oil collection rate of 29 gallons per minute and a throughput efficiency of 78%. This performance was achieved with a belt speed of 25 8/10 RPM and a backplate opening of 4 3/4 inches. In 1-foot random waves, the best performance was an oil collection rate of 20 gallons per minute and a throughput efficiency of 54%. This was achieved with a belt speed of 10 4/10 RPM and a backplate opening of 5 1/2 inches. During Phase 2, the following was accomplished. Support equipment for oil containment booms was identified and tested. Standard test procedures were developed and validated. An improved oil containment boom was developed and tested. And optimum operational parameters were identified for oil skimmers. The tests documented by this film and a companion written report are part of the Navy's continuing effort to eliminate pollution caused by oil spills. In Phase 3, already underway, the Civil Engineering Laboratory will conduct harbor evaluations of boom mooring systems, boom utility craft, and cold weather performance of oil spill cleanup systems. Evaluation of oil spill cleanup equipment will continue to further define confidence intervals of the performance data obtained during the Phase 2 tests. Cost-effectiveness studies will be conducted on selected systems for typical oil spill scenarios.